Alright, Assalamualaikum and good day again. We will start with our lecture 6. Today we will be talking about statics of rigid bodies. Okay. Basically, before we talk about static for rigid bodies, we have to talk about moment first, right? So let's say this is you, right? Before the class, you do some exercise, stretch a little bit, and you lift one of your arm, all right? And we know we have a weight attached to your arm. Okay. And since you are able to lift your arm and hold it uh, in place, so that means the summation of force should be equal to 0, or basically your arm is in equilibrium. So we have the reaction at the shoulder of your arm. And since your arm is not moving, R must be equal to weight, or basically it is in equilibrium or in static condition. Your arm is not moving, all right? And then you have your other arm. Again, this arm has about the same mass attached to it. So you have weight of the arm. And again, you have reaction at your shoulder, R, which is also equals to the weight, since your other arm is also not moving. So both of your arm are in static condition. However, the arm that you have lifted will felt another thing instead of just simply force. You cannot hold your arm in this position for long. Okay. Uh, After some time, you can't bear it anymore. Okay. What's happening here? Instead of having just the weight or the force acting on your arm, you have another effect of this force, which tends to rotate your arm. Okay. So that it will be in your resting position, basically downward like this. Okay. So if we want to quantify that, we are seeing something like this. All right. So we have a rigid body, AB for example, and we apply force F at point A. And then this force F will be felt at other point as well. So in this case, this force F is felt at point B, okay, with the same magnitude F. But not only that, the effect of this force F on B will be added at point B. And that effect is what we call as moment, okay, moment at B. Basically, a rotational force that tends to rotate the rigid body about point B. Okay, and this is what we call as moment. In terms of equation, this moment can be written as simply as equals to force times distance in 2D form, or distance times force. Okay, the arrangement does not matter in 2D form. Okay, however, in 3D form, the arrangement does matter. All right. So in 2D form, we know that the object will rotate on a plane. So basically on this particular plane here, right? In a 2D plane. And the rotation can be either clockwise or counterclockwise. All right. The direction of rotation will depend on the direction of force as well as our point of moment. Okay. One thing to note here, this moment is actually point dependent. So that's why here we stated clearly this moment is moment at point B. All right, moment at point B. So force F acting at A will cause a moment at point B. And the magnitude of that moment is given by MB equals to force times D. D is what? D is a perpendicular distance from the line of force. Okay, this is your line of force towards the point of moment. Okay, this is your point of moment. Since we are talking about point B, so B is our point of moment. All right, and F will be the perpendicular distance. Perpendicular means it is at an angle of 90 degrees from the line of force towards the point of moment. And D happens to be our shortest distance as well. Alright? So remember, moment at any point is equals to force times D. D is the distance, the perpendicular distance or shortest distance from the line of force F towards the point of moment. Okay? It can be B or any other point. Alright? So if I want to give another example, instead of taking moment of point F towards point B, let's say we consider another point C, for example, here. All right. So what would be the moment at point C due to this force F? Okay. The moment point C will be equals to, again, OF times the perpendicular distance, basically this guy here. Let's say, for example, say I just give another name here. Let's say this is equals to E, right? So F times, okay. And this force will cause a rotation that is clockwise with respect to C. So the direction of the rotation is clockwise. All right, clear? Okay. So in terms of magnitude, which one is larger, MB or MC? Anyone? Okay. In terms of magnitude, we will see that MB will be larger because D is way larger than E. Okay. So MB will be larger than MC. All right. So for a moment will depends on force as well as distance from the line of force towards the point of moment. Okay. Is there any point that will give us zero moment? Which point give us zero moment? Point A will give us zero moment. Okay. Why? Because based on our equation here, F is not zero, but D is zero. Okay. So F times zero D will give us zero moment. Okay. And the unit of moment is equals to Newton times unit of distance, or in this case, meter. Okay, so you have unit of moment as Newton meter. Okay, so again, moment is a vector quantity. All right, so it will have magnitude. Okay, so the one that we have calculated before here. Okay, this is the magnitude of it, and this is the direction of the moment. Okay, so this part here is the magnitude of the moment. This is the direction of the moment. Right? In 2D space, it is enough for us to describe the direction as clockwise or counterclockwise. However, in 3D space, uh, clockwise or counterclockwise might not be accurate enough to describe the motion of the moment. So in that sense, we have to use IJK. Okay, at the moment, it's enough for using clockwise or counterclockwise in 2D space. All right, clear? Okay, let us solve one example. Okay, let's say we have force 100 Newton acting at A, and we want to find what's the moment at B. Okay, again, we know that moment at B should be equals to the force. Let's say this is F times the perpendicular distance from the line of force to point B. So your first task is to determine what will be the perpendicular distance. Okay, so this will be the perpendicular distance or shortest distance from the line of force towards point B. Okay, so once we have determined that, we can write moment at B equals to 800 times D. D in this case is equals to 7 plus 3 here. Okay, so 7 plus 3. So we have 800 times 10 equals to 8,000 Newton meter. And this force F is causing a rotation that is clockwise with respect to point B. Okay, or basically it tends to rotate the object clockwise with respect to point B. Okay, Yeah? Everyone is clear about this. Very simple, right? Okay. Now we move on to something much more interesting, right? So in this case, we have two forces, 520 Newton and 400 Newton. Okay. The 520 Newton force is acting at A, 400 Newton force is acting at B. Now we want to determine what will be the moment of the forces at point P. Okay. So where's P? P is here. All right. So we have two forces here. Moment at P, let's say I give a name here. This is F1, F2. Okay. So moment at P will be equal to F1 times D1 plus F2 times D2. What is D1 and D2? D1 is this is the line of force for F1. Okay, so quite long there. This is the perpendicular distance, okay, respect to point P for F1. So this will be your D1. And then we have, this is the line of force for F2. So the perpendicular distance or shortest distance will be this distance. This will be your D2. Okay, so moment at P will be equal to the sum of moment due to F1 and the sum of moment due to F1 and F2. Okay, clear? So our task is to determine what will be our D1 and D2. Okay, F1 and F2 are given in the question. So we can use our mathematical skill to determine what's the angle and try to deduce what's the value of D1. Okay, let's say we start off with D1 first. So this is our D1. Okay, so we want to know what's the length of D1. Okay, how to determine the length of D1. Okay, let's say if this is angle theta, so the same angle here applies. Okay, same angle theta. And then with this length here is equals to 10 minus this length here. Okay, minus this length as well. All right. However, in this case, we want to find D1. We do know the angle here is 90 degrees. So if this is theta, this portion here should be equal to 90 degrees minus theta. Right? So how do we go about in solving this? This is 40 degrees. So we can determine what's the length here. So this length here will be equal to 4 sine 30 degrees. Right? So what is the length here? Can we determine that length? Then we know the angle. That's for sure. Okay, it's quite difficult to determine D1. Okay, it's because in this case we don't have additional information here. Okay, so instead of calculating for D1 straight away like this, we can resolve this part of the equation to another form. Okay, which is equals to instead of we have only F1 here, we write in terms of F1 along X times dy or d1y plus F1 along y times d1x. Okay, so this term is decomposed into this form. All right. So what's happening here? Instead of having our F1 equals to 520 Newton, we'll look at the component of F1 along X and Y axis. So along Y axis, this will be F1 Y. Along X axis, this will be F1 X, right? And we know that F1 times D1 should be equals to F1 X times the perpendicular distance from the line of F1X towards point D, in this case, this guy here, and this is your D1Y, YY was along Y axis, right? So that's why we have F1X times D1Y, and then plus F1Y times the perpendicular distance from the line of F1Y towards point F, this is our D1X, okay? So what happens if you forget which is which? It doesn't matter. Okay, just decompose this F along X and Y, and remember to multiply the force with the perpendicular distance from the line of force towards point of moment. So basically, if you are looking at this component here, F1X, this guy, it must be multiplied with the distance that is 90 degrees with respect to the line of force. So basically, this guy here is 90 degrees, right? So this distance represents a perpendicular distance from F1X towards point P. The same goes for D1X, all right? So if we have F1Y along this line, so the perpendicular distance will be this distance, okay, perpendicular to the line of force towards point of moment, in this case, point P, okay? So instead of calculating F1D, okay, we resort to calculate F1X D1Y plus F1Y D1X. Okay, why we do this? Because sometimes it is difficult to determine one of the parameter, for example, in this case, D1. Okay, so that's what we are doing right now. So F1X is just equals to F1. Component along X is 520 times sine of this angle. Okay, so what we have a triangle like that. 5, 12. Here is 13. Okay, this is a typical right angle triangle. Okay, so we want to know what's the angle of this, what's the sine of this angle, right? To determine the component of F1 along X. So that will be equals to 520 times. Okay, let me go about this slowly. Sine of the angle theta, which is equals to 520 times 5/13, right? Newton. That's our F1X. Of course, in this case, I can put a negative sign here since it is pointing towards negative x-axis and whatnot. But our aim here is not to calculate the magnitude of force, but instead we want to know the moment due to this force. Okay, so putting negative here might not be so important. All right, so I normally ignore this negative. Okay, what I'm writing is just the magnitude of F1X. Okay, so that's why everything here is positive. And then I will calculate what is the magnitude of F1Y. That will be equal to 520 cos theta, or 520 times 13/12. Why is it 5/13? For sine theta or cos theta? Sine theta. Okay. So let me draw this triangle on a much bigger scale. This is theta, right? So this is 12, this is 5, 90 degrees, this is 13. Right, sine of theta should be equals to 5 over 13. Cos of theta equals to 12 over 13, right? I see this a lot. Sometimes students uh, don't don't like to use this format. Okay, they are more comfortable in figuring out what's the angle theta. So they waste their time finding out what's theta. Theta is equals to, let's say, if they know this is 5, this is 12, they calculate what's the value of theta, which is equals to 5 tangent minus 1, 5 over 12. So once they got theta, they punch it into the calculator to calculate what's the sine theta or cos theta. You can do that, but for me, it's a waste of time because you can actually calculate directly what's the value of sine theta and cos theta based on the given triangle. Okay, we don't require the value of theta, okay, but we do require the value of sine theta and cos theta to determine what's the component of f1 along x and y. So that's why I don't bother to calculate what's the value of theta. All right. So once we have determined f1x, f1y, their magnitude, and then we can start to look into d1x and d1y. So d1x is the distance from P to A along y-axis. In this case, it is fairly simple. You have 10 for this portion here, plus this portion should be equals to 4 sine 30 degrees. Right? So and this will give you your d1x. d1y is equals to this distance, or basically 4 cos 30 degrees. Right? Once we have this, we can calculate this portion of MP, which is f1 times d1. So that's what we are going to do. So f1 times d1 now is equals to this part here, okay? 520 times 5 over 13 f1x times d1y 4 cos 30 degrees. All right. And then we have another portion here. Plus. So instead of putting the sign, let me remove the sign first. So we have f1y 520 times 12 over 13. And then we have d1x 10 plus 4 sine 30 degrees. Okay. In terms of sine, what we are calculating here is basically moment. Okay, this guy is moment due to f1 at point P. Okay, we are calculating moment due to f1 at point P. All right. So that means we want to know what's the direction of this moment here. Okay, due to f1. So the direction of moment can be simply obtained from the direction of force with respect to point P. Okay, so let's say we consider the first part here, which is f1x times d1y. So look at f1x. Okay, f1x, when we apply this at A, when we apply this, the moment created at point P, or basically what will this f1x do to point P? It tends to rotate the object clockwise. So this part is rotating the object clockwise. Okay, so to make it simple for us to determine the direction of moment later on, we assume certain positive direction. Let's say we assume that the direction of moment is positive clockwise. So f1x, okay, will cause a clockwise rotation about point P. So the sign here is positive for f1x times d1y. Okay, for f1y times d1x, f1y times d1x, okay, f1y will create a rotation that is counterclockwise with respect to point P. So the sign is negative. Why negative? Because we are saying the moment is positive clockwise. Okay. That's how we know the direction of moment. Okay, for this uh, f1x and f1y. All right, clear? Okay. Next, we'll be calculating f2 and times d2. So this is our f2, and this is the line of force for f2. Right. So the perpendicular distance respect to point of moment, point P, will be this distance. So this is our d2. All right. And this distance can be determined easily compared to d1. So f2 times d2 will be equals to, the magnitude is 400 times the perpendicular distance, or the shortest distance. This is equals to 3 plus 4 cos 30 degrees. Right? So straight away we have our moment due to F2 at point P. Okay. But here is moment due to F2 at point P. Right? So once we have that, we can straight away calculate what is our MP. So moment at point P is equals to F1 D1 plus F2 D2. Okay. So from our previous equation, if we want to calculate this, we will have, so can somebody calculate this for me, please? Anyone? Negative 1.8. All right. So this is F1 times D1. Okay. In this case, this minus sign is for rotation that is clockwise, positive. All right. So make sure that your uh, assumption of positive rotation are the same. So that's why we have minus sign here. Okay. And F2 times D2 will give us, two five eight 5.64. Is it? Positive. Right. So in the end, moment at point P will be equals to, add these two terms together. Anyone? All right. So basically, this is how we calculate the moment at point P due to 520 Newton force and 400 Newton force. Okay. So next we will be talking about couples. Okay. Uh, Previously when we talk about moment, I keep stressing that the moment is point dependent. Okay. Let's say if we are talking about point B, so the moment should be written as moment at point B. Okay. And this should be equal to force times distance, and this distance needs to be from line of force to point B. Okay, so this is very critical. All right. However, in some instances, we can have what we call as free moment, or we call it as couple. All right. And why it is free? Because it is no longer dependent on points. Okay. It is free because it is no longer dependent on point. Okay. No longer point dependent. So basically, the moment will be applied to the whole body. Right. It tends to rotate the whole body. But basically, any points on that body will felt the same amount of moment. Okay. Uh, we will have this free moment or couples when we have a pair of force. Okay. Pair of force. And not just any force. This pair of force should have equal magnitude. Okay. So it should have an equal magnitude in opposite direction. Okay. In opposite direction. So one can be upward, the other one downward, or one to the right, the other one to the left, and so on. Okay. In opposite direction. And both of them should be in parallel line of action. Parallel doesn't mean it needs to be in one line. Okay, it just need to be in parallel line. So for example, if this is your F1, you can have another F2 as long as both of them, okay, is parallel. So parallel line of action. So if generally you have these two forces, F1 and F2, they are not coupled. However, if we are saying, okay, this F2 is equals to F1, so now you have couple or a pair of force whereby you have two force with equal magnitude in opposite direction, okay, in opposite direction, and acting um, at a parallel line of action. Okay, so both of these force lines are parallel. Okay, so if we look at one example, our rigid body, so we have this as our rigid body, and let's say we have 100 Newton force being applied at A and another 100 Newton force being applied at C. Okay, both of them are along parallel line of action. Okay, parallel lines. This is parallel lines. All right. Since the forces having equal magnitude, acting in opposite direction, one upward and one downward, and they are acting along parallel lines of action. So these two will behave or will becomes a couple. Okay. So when it becomes a couple, if we look at any point, the moment about any point on this rigid body will becomes the same. Okay. For example, if we look at point A, so the moment due to 100 Newton at A will be equals to 0. Why? Because this 100 Newton is passing through point A. Our perpendicular distance is 0. D is 0. However, we will have moment due to this 100 Newton force at A. And that moment will be equals to 100 Newton times the perpendicular distance. Perpendicular distance will be this distance from the line of force towards point A. Okay, and this distance is equals to 4. So you have 100 times 4 equals to 400 Newton meter, and the rotation is clockwise. And if we are saying clockwise is positive, so the magnitude is positive 400 Newton meter. Okay, that is for moment at point A. Due to, sorry, that is the moment that we get at point A. Now, if we consider another point B, for example, okay, so point B is here. So both of these 100 Newton force will create a moment at point B. So we will have for this 100 Newton force, this as our perpendicular distance equals to 1. So we'll have 100 times 1 Newton meter here, and the rotation is clockwise, so it should be positive. So this is the first part. And then we have another 100 Newton times the perpendicular distance. Now the perpendicular distance is this distance, which is equals to 3. 100 times 3, you have, sorry, I got it. Previously, we have this part here. Okay, now we have 100 times 3. Okay, again, the rotation about point B is clockwise again. So we have a positive sign here. So we add these two terms together, we will end up with the same 100 Newton meter. And you can go on at point C, point D, you will still have the same moment acting on this rigid body. In fact, you can go any other point that you like. Okay, on top of this rigid body, you will still get the same magnitude of moment with the same direction. Okay, this moment is what we call as free couple. Why free? Because it is acting uh, at the whole body. Okay, it's not limited to any points. Okay, so we can have, for example, something like this. Okay, 90 Newton at point A to the left, another 90 Newton at point C to the right. These two will construct a couple. Okay, uh, they will create a free couple. Okay, and that free couple will be equals to 90 times 4, right? Equals to 360 Newton meter, and the rotation is counterclockwise. Okay, how do we calculate this? Okay, you just take the moment, let's say along this line, let's say at point B, since this 90 Newton is passing through point B, so you will have no moment due to this 90 Newton. You have only a moment due to another 90 Newton here. Okay, so 90 Newton times the perpendicular distance 4, you will have 90 times 4 equals to 260 Newton meter. And the rotation is clockwise. Okay, and if we proceed here, again, we'll have a rotation. In this case, these two are acting along parallel lines in opposite direction, okay, with equal magnitude. So it will create a free couple, which is equals to 120 times 3, and this is equals to 260 Newton meter again. All right. So both of these are the same amount of moment, but given through different magnitude of force acting along different direction as well. Okay, the same goes here. Okay, if we want to extend example further, so we have 3, 4, this is 90 degrees, so this line is 5. So again, this 72 Newton meter and 72 Newton force will create a moment, and that moment is creating a rotation clockwise again. So the moment is equal to 72 times 5, which will give us 360 Newton meter again. Okay, again, it's the same free couple. Okay, given through different type of force. Okay, or we can just straight away draw. Okay, we have a free couple which is equal to 360 Newton meter. Okay, we can put the free couple at C or arbitrarily here. It doesn't matter. Okay, sometimes we put at one point, sometimes we just put in between. Okay, it doesn't matter because this free couple is transferable. It is acting at the whole rigid body. It's not at point C per se. Okay, it is acting at the whole rigid body. Okay, so sometimes we also draw it in this form. Okay, so we have two arrows. Okay, and one perpendicular distance in between the arrows. Okay, this also represent the free couple. Okay, and the direction of rotation is still the same, which is counterclockwise. Right? If we have more than one free couple, for example, acting on one rigid body, in this case, one at point C, we have 20 Newton meter counterclockwise. At point A, we have 60 Newton meter clockwise. Okay, so in total, the sum of these two couple will give you couple equals to 40 Newton meter, and it is acting clockwise. Okay, so you can just add up the contribution of the free couple on that rigid body. Okay, so it is not location dependent anymore. Okay, it is just a scalar value. All right. Same goes here. If we have 20 Newton meter counterclockwise and another 60 Newton meter counterclockwise, we add both of them, we will have 80 Newton meter counterclockwise. Okay. Again, if we add clockwise with clockwise, we will have an increase in magnitude. or if we add counterclockwise with counterclockwise, we have an increase in magnitude. But if we add clockwise with counterclockwise or counterclockwise with clockwise, we will have decrease in magnitude. Okay, so we have to consider the direction of the free couple when we do the addition. Okay, once we have known the concept of free couple, now this effect makes sense to us. Okay, remember this diagram that I have shown earlier. When we have a force being applied to A at B, okay, if we look at B, we are seeing that B also felt the same force, but with addition of the effect of this force F at point B, and that effect is given by this moment at B. Okay, why we have this moment at B? If we look at the rigid body shown here, let's say we have force acting at O at the angle of theta. All right, at A we have no force at all, or in this case, the summation of force at A equals to 0. So in that sense, we can add back two force that are equal at point A. Okay, let's say in this case we give a force F at point A, but acting at opposite direction. And since we know these two forces have equal magnitude in opposite direction, they will cancel out, and in the end becomes a zero force A. Okay. However, once we do this, we start to see that this portion of the force and this force will create a couple. Okay, so instead of having these two force, we can replace this as a couple. All right, a couple meaning can have a moment that is rotating counterclockwise, and this moment can be placed anywhere. And if we want to look at point A, for example, okay, so that means A will felt the remaining force here, which is this force F, that is not cancelling with anyone. Okay, so at A we will still have this F plus this free couple here. Okay, so the free couple or the moment can be placed at point A. Okay, because it is actually acting anywhere on the rigid body. So point A will felt the force and the free couple or the moment, which is equals to F times D. Okay, F times D. F times D. D is our perpendicular distance from the line of force towards the point of moment. In this case, our point of moment is point A. Okay. So the forces is sum up this F. You have okay, the F is still the original F. Okay, it's just that instead of having the F at O, now the F is at A. Clear? This is what we call as equivalent force couple system. So initially we have force at O. Okay, so if we want to transfer the effect of this force at A, so the effect will be at A, you will have the force F plus moment due to F at A. Clear? Okay. Okay. If I go back to our uh, arm example like this, okay. So if we compare both arms, okay, your right arm and your left arm, what's the difference between these two? At your uh, left arm, the line of force is along the same direction. Okay, so basically here you have summation of force equals to 0. Fine. Okay, and summation of moment also equals to 0. Why? Because moment is equal to F times D. Okay, so if we take any point as your point of moment along this line, D will still be equal to 0. However, in this case, okay, if you want to see what was the effect of this weight at your arm location, okay, so here we are seeing summation of force still equals to 0. Okay, because weight is opposing your reaction at the shoulder here. Okay, and not only that, we are seeing that okay, this weight will have another effect to your shoulder, and that effect is given by the moment, which is equals to weight times this distance d. Okay, at your shoulder. So if we want to replace what's the effect of the weight at the shoulder, okay, what we have, we will have, oops, and at the shoulder you'll have the weight plus the moment due to this weight, which is equals to the weight times d. Okay, so this is what we call equivalent force couple system. Right, initially the force is here. We want to know what's the effect at another point on the rigid body. So this will be the equivalent effect of it. Okay, so let us look at one example. So here we have a rigid body, okay, and it is being acted on by two forces and one free couple. Okay, so this 148 Newton meter is a free couple. Why? Because it's given in this form, so you have rotation counterclockwise. Okay, it's not moment at A or at any point, so this must be a free couple. So we want to replace all the forces and the moment acting on this rigid body with equivalent force couple system acting at O. Or basically, we want to know what's the effect of all these forces and moment at point O. So what we want to have, say this rigid body and this point O. Okay, we want to know what will be the sum of forces here and what will be the sum of moment at point O. Okay, or this is the resultant at point O, basically. All right, so in this particular example, what we need to do, we need to solve for resultant at point O plus summation of moment at point O. Okay, so let us solve for resultant first. So we want to find resultant at O. In this case, we have two forces. Okay, so resultant is equals to, if we want to do it along x and y axis, we can say, okay, it is the sum of component along x and y. So Rx should be equals to 120 cos 60 degrees. Done. Okay. Only this 320 has a component along x. 400 Newton has no component along x. Then Ry is equals to minus 400 minus 320 sine 60. Right? So our R is equals to Rx squared plus Ry squared. Square root of that. So we will have, in this case, R equals to, I'm getting the magnitude of R equals to 695.78 Newton. Okay. So if we want to know what's the angle of R, normally I will draw Rx and Ry first. So this is Rx, positive value, that's 60. And then we have Ry. Okay. And Ry is a negative value, equals to 695.78. So this will be our R. And the angle or the direction will depend on us. Let's say I'm taking this as the angle of R. So theta is equals to tangent minus 1 695.78 over 160. So I'll end up with theta equals to 77.05 degree. Okay, so this is the angle of R. Next, we want to find the summation of moment at point O. So the moment will be coming from 400 Newton, 320 Newton, as well as this free couple here. The moment at O, let's say again, positive clockwise, is equals to the free couple, negative 148, y negative, since it is rotating counterclockwise, and I'm taking the assumption that rotation clockwise is positive. And then we have this moment due to the 400 Newton force, the line of force, the perpendicular distance is basically distance here. This is your D. Okay. The magnitude of the moment will be equals to the rotation here is clockwise, so it must be positive. 400 times D. D is 160. Or if I want to make everything in terms of meter, this will be 0.16 plus the angle here is 30 degrees, so component of OB along horizontal axis will be 0.15 cos 30 degrees. Okay, so this is the moment due to 400 Newton meter at point A. At point, we are looking at point O. Okay, my bad. O, simpler then. And then we have moment coming from this 320 Newton meter. Okay, and if we look at the angles given, yes, 60 degrees. This is horizontal axis, this is vertical axis, so the angle here must be 30 degrees. Okay, and if it is 30 degrees here, the angle here is 90 degrees, the angle here is 60 degrees. So 60 plus 30, that means you will have here a right angle, obviously 90 degrees. So this 320 Newton meter is acting at an angle of 90 degrees with respect to line OC. Okay, so that means our D for 320 Newton force will be OC. Okay, this is D for 320 Newton force. That means I can straight away write the moment due to 320 Newton force is equal to 320 times the D. D is just the length of OC, which is 0.5 plus 0.15. Alright, so calculate this. We will have M and O equals to am I right? Okay, very small moment here. Almost close to zero. We have 148 minus, okay, fine. 400 times 0.15 cos 30 degrees, okay, also fine. 120 times 0.3. Okay, anyway. So our equivalent force couple system at point O. So our final answer will be so R is 695.78. theta will be equals to 77.05. And of course, we have moment, which is having a magnitude of 0.04 Newton meter. Okay, and it is rotating counterclockwise. Of course, if we want to use positive clockwise convention, the magnitude is equal to minus 0.04 Newton meter. Okay, so this will be your equivalent force coupled system. At point 4. Okay. Next, we'll be moving into a moment about a point in 3D. Okay. So in 3D form, just like what I mentioned earlier, the order of operation is very important. Okay. Why it is very important? Because we know that moment is a vector quantity. We have your distance d, okay, in the form of vector r. Our position vector is also a vector quantity. Same applies to f. F is also a vector quantity. And in 2D form, we can simply write moment is equals to distance times force. Okay, so this dot here represent a simple multiplication. Okay, however, in 3D form, in IJK, okay, we don't have this dot operation here or simply simple multiplication here. We are having a cross product. Okay, and cross product is very sensitive on the order of vector. Okay, if you have force cross r or f cross r, it will be different or in opposite direction compared to r cross f. Okay, so always remember moment at a point should be equals to r cross f. Okay, r is our position vector or distance vector. Okay, f is our force vector. All right. What's the difference between r and our d previously? Okay, in the case of 2D, let's say I draw our rigid body again. Let's say this is our force, right? And we want to find moment at this point here, point A. So moment at A will be equal to force times D. D is our shortest distance or perpendicular distance from the line of force towards point of moment. Okay. Can we use this as our D? No, we can't use this as our D because it is not perpendicular. Okay, when it's not perpendicular, we can't use this as our D in 2D form. All right, D need to always be perpendicular to the line of force. All right. However, the beauty of using IJK is that our D or our distance vector can be represented by a position vector which starts at the point where the moment is taken. Okay, remember, start, okay, from the point where moment is taken and ends at any point. Any point. Remember, any point on the line of force. All right. R starts where the moment is taken and ends at any point on the line of force. All right. And of course, this R can be written in terms of IJK. So you have Rxi plus Ryk plus Rzk. And our force, of course, can be written in terms of Fxi plus Fyj plus Fzk. Okay. So our moment at any point, okay, will be equals to the position vector cross with force vector. And once we have cross product here, We cannot run away from looking at what happens if we have I cross J, J cross K, K cross I, or I cross K, and so on. Okay, normally this is what I normally write when I solve this kind of cross product. Here I have I, J, K. So always remember the positive direction is from I to J to K, and it continues. For example, if I have I cross J, I will have a positive K. Why is that? I cross J, positive K. And if I have J cross K, J cross K, I will have a positive I. Okay. In fact, if I want to go further, if I have K cross I will have a positive J as well. Alright. So as long as it is following this order, IJK order, you'll have a positive value. Okay. Once the order is being reversed, you'll have a negative value. For example, instead of having I cross J, now I want J cross I. So J cross I will give us negative K. Or I can have I cross K. I cross K, now we'll have negative J. And K cross J will give us negative I. Okay, K cross J will give us negative I. Alright. And the direction of this moment about a point will follow our right thumb. Okay. So this is the direction of moment. Okay. And its rotation will be following the curl of our remaining finger. Alright. Why is that? Okay. To give you a very simple example, let's say we have our well-known X, Y, Z axis, right? So unit vector along X is I. Unit vector along Y is G. Okay. So let's say you don't know where is the direction of Z axis, right? So we can use the cross product information. We know that I cross J will give us a positive K, or along positive Z axis, right? So I cross J, mathematically what happens here? We have vector I cross vector J. So I cross J, okay, I cross J will give us positive K. So the positive K will be along this direction. This is your positive K, right? Positive K direction. And K must always be 90 degrees with respect to the plane containing I and J. So that's how we know that the angle between the Z and X axis must be 90 degrees. And the angle between Z and Y axis must be 90 degrees as well, right? It's based on this cross product, right? So remember, IJK will give you the direction from I to J to K will give you a positive direction. If you reverse this, it will be negative. And moment at a point is equals to R cross F, not F cross R. Always moment equals to R cross F. Never mix this up, okay? R must come first, followed by the force vector. Okay? Yep. The right hand thumb, okay. So if I want to draw your right hand thumb here, okay, pretty challenging here. This is your thumb. Okay, so this is your thumb, right? Remember, this thumb is the result, the direction of moment, right? So if I have I cross J, I will have positive K. How do I know positive K is along this direction? Follow the thumb. So this is your thumb, right? And how it rotates, it will follow the curl of your remaining finger. So this is the direction of rotation. I cross J. Make sense? Okay. That's why we use this representation to determine the direction of moment. Okay. All right. So let us look at one simple example. Let's say we have a force F equals to 10 Newton. Okay, so this is your force F. Magnitude is 10 Newton. Fine. Now we want to find the moment due to this force F towards some point. Okay, let's say for example's sake, we want to find moment at point B. Okay, for example, moment at point B. Okay, so want to find moment at point B. Okay, so moment at point B will be equals to R from B. Okay, remember position vector must be starting from point of moment B towards the line of force. Where's our line of force? This is our line of force F. Okay, so from B towards the line of force, okay, we can choose multiple points on top of this force F here. In fact, I can even extend this F further. This is the line of force. Okay, we can choose RB to be from B towards any point on top of this line of force. Any point. Okay, so in this case, we know explicitly point C and point D. Okay, the coordinate of point C and D is known. All right, so you can use RBD, or you can also use RBC. Okay, so the choice is up to you. Both are possible. Or in fact, if you are adventurous, you can choose any R from B towards the line of force. Okay, it will still give you the same answer. But normally, I will always advise students to choose the simplest RB. Okay, simplest R. Why? Because it will make your life easier. Okay, so for example here, if we consider points C and D, okay, we will not be considering somewhere here. It's quite difficult to visualize that. Okay, let's say if we compare RBC and RBD, if we want to write RBC and RBD in terms of vector, okay, RBC is from B to C, right? So in terms of IJK, the position vector will be equals to, along X, it is minus 2.4 I. Along J, it is equals to, the height is 2.4 to 2.4 plus 4.4 J. Along Z axis, it is 0. Okay, 0K. For R, PD, our vector now is equals to, again, minus 2.8 I. Okay, 2.4 plus 0.4, 2.8 I. Along y-axis, it is equals to 2.4 only plus 2.4 J. However, this time around, we will still have component along the axis. So plus 2.2 J. Okay, so you have two choices here. One is to use RBC that has only two components along I and J. The other one is to use RBD that has three components along I, J, and K. Okay, of course, if you choose RBC, your calculation step will be much simpler because you don't have component along K. Alright, so this is what I meant by choosing the simplest position vector R. Alright, so in this case, we will choose R, B, D. Okay, because it is the simplest. Alright, for this particular example, we will try both to show what's the effect of choosing RBD instead of RBC. Okay, so that's what we are going to do. Okay, so for the first step, now let's try the hardest one first. Okay, RBD cross F. Okay, so we need to find RBD. Okay, we have determined RBD. Fine. The position vector. We need to determine F. Okay, so F needs to be written in terms of IJK. Okay, and we have learned how to write F in terms of IJK before. So F is from C to D. Okay, and coordinate of C is known, which is equal to 0. Okay, along X is 0, along Y is 2, along Z is equals to 0. Point D, the coordinate is along X minus 0.4, along Y 0, along Z axis is equals to 2.2. Right? So once we have known this, we can determine F in terms of IJK. F will be equal to its magnitude 10 times the X over D I plus dy over d k plus dz over d k. Okay, so just substitute the values here. So dx will be equals to dx, since we are starting from C to D. So dx will be equals to minus 0.4. Okay, we will be calculating d later on. dy from 2 to 0. Okay, from 2 to 0, again minus 2. Okay, plus, okay, dz, set from 0 to 2.2. Okay, 0 to 2.2. So we have 0.2. Okay, if you are not clear how do I get dx, dy, dz, simply take, okay, the value of coordinate x at point D, which is minus 0.4, minus coordinate x at C. So minus 0.4 minus 0, you'll have minus 0.4. Next, you have along y, dy will be equal to 0 minus 2, so we have minus 2. Along z, you have 2.2 minus 0, so we have 2.2. Okay, so d is equals to 0.4 squared plus 2 squared plus 2.2 squared. The sum of that will give you one value. Take a square root of that sum. So 0.4 squared plus 2 squared plus 2.2 squared. So you'll end up with d equals to 3. Okay, so this is your f in terms of IJK. Done. All right. So now we want to calculate MB. So let's say we start our calculation somewhere here. So MB is cross product between RBD, which is minus 2.8 I plus 2.4 K plus 2.2 K. Cross product with this guy here, which is minus 4 over 3I minus 20 over 3J plus 22 over 3K. Okay, I simplify this by multiplying 10 with the term inside this bracket. So we need to do this cross product, right? And remember, to do the cross product, we have to follow the convention of positive sign I cross J equals to positive K. Okay, this order. So we have to do it one by one, right? Let's say I consider 2.8I first. Okay, so 2.8I multiplied with negative 4 over 3I. Okay, okay, I forgot to mention one thing about cross product. You can have values when you cross I with J, J with K, or basically I with other than I. Okay, if you cross product I with I, you'll end up with 0. Okay, j with j will give you 0 as well. K with k is 0 as well. Okay, so you will have values only when you cross product in between I, j, k and not with itself. So I must be cross product with j and k, not with I. So here we have minus 2.8 times 20 over 3. Okay, so ij will give you a positive k, right? And then ik, we have minus 2.8. K is 22 over 3. Ik, negative j, right? Continue further. Now we have done with I. Look at j. No enough space here. Okay, bring it here. So mb is equal to minus 2.8 over 3 a minus 2.8 22 over 3 minus j. Okay, this is for item, right? Let's take a look at the j term. So we have plus 2.4j, sorry, 0.4. J must be multiplied with I and K. 0.4 times minus 4 over 3. Ji will give you minus K. Right? Next we have J with K. So you have 2.4 again times 22 over 3. Now JK, JK, positive I. Okay. If you are used to this, you don't need to refer to diagram anymore. Right? In case you keep forgetting, just draw diagram and refer to it. And lastly, we have 2.2k. So we have plus 2.2 times minus 4 over 3. Ki will give you positive j. Again, 2.2 times minus 20 over 3. So kj will give you minus I. Okay. So once you have this, so you can calculate what's the value. So you have some term in front of I plus some term in front of j plus some term in front of k. Okay. So this will be your moment at point B. Okay. I don't want to waste our time to calculate this. Okay, you can calculate this at your own leisure. I just want to show how complicated it is when you choose the wrong R. Now let us solve this again using much simpler R, in this case RBC. Okay, in this case, we will be using RBC. Okay, our force vector will still remains the same, right? It's just that we change the position vector. Okay, so MB now is equal to RBC, which is this guy here, minus 2.4I plus 4.4J, cross with the same force vector. All right. So if we want to solve this, so MB equals to, let's say we consider the item first, minus 2.4 times minus 20 over 3. Ij will give you positive K. And then we have 4.4 times 22 over 3. jk will give you positive I. Sorry, I should be following the same term first. So 2.4 times j, okay, will give you positive k, I, j, k. And then we have minus 2.4 again times 22 over 3 ik will give you negative j, right? Next we have the j term, j times I. J times I will give you negative k. And then we have 4.4 again times 22 over 3 jk will give you positive I, right? So you can solve this. Again, you'll have some term in front of I plus some term in front of j plus some term in front of k. Okay. Now, if we consider the amount of calculation needed to solve for MB by using RBD compared to RBC, okay, you are seeing here that you have additional step here, right? The additional step means additional work. It also means additional place that you can, additional source of error, okay, basically. So this one is much simpler and much faster to solve. And in the end, you'll still end up with the same value of MB. Okay, so always remember to choose R that is the simplest to solve. Clear? Any question on this? Any question? No question? Okay. Since everything is clear, I will proceed with moment about an axis. Okay. So what's the difference about moment about a point and moment about an axis? In 2D form, okay, actually what we are calculating, okay, even though we don't stress this a lot, in 2D form, let's say you have x, y plane, this will be your z-axis, okay. When we have a rigid body, for example, this is your rigid body. We have 2 points here, point A, point B, and let's say you apply certain force F within this xy plane, okay, so this is force within xy plane. We can get moment about A, which is equals to force times the perpendicular distance from point of moments towards the line of force. Let's say this is the perpendicular distance, okay, D. So in 2D form, we know that moment at A is equals to D times this force. Okay. What we don't tell you is what we are calculating here is actually a moment about an axis. Okay. And that axis is out of this XY plane, or basically along the axis. So that's what you are getting here. Okay. So you are getting something like this. Okay. So this is the moment at A, which is about Z axis. All right. So in 2D calculation, basically this is what we are calculating, moment about an axis. Okay. Although we don't say it is about an axis, we say about a point, because that axis is also passing through the same point. So it makes no sense to say it is about an axis since you don't see the axis in 2D plane. Okay. In 3D plane, yes, we are seeing that axis. All right. So that's why we have a distinction between moment about a point and also moment about an axis. Right. Moment about a point, this guy, is a vector quantity. All right. Moment about point is a vector. So basically, moment will have a component along I, j, and k. Right? The moment will have a component along I, j, and k. All right? Since it is a vector. Moment about the axis will give you magnitude. Okay? It will give you magnitude. Why is that? Because of this. Here we have a dot product. Okay? If you remember from mathematical class, dot product will give you uh, magnitude or scalar. Okay? So what we have here, moment about the axis is equals to a unit vector along the axis. Okay? Times moment at a point on that axis. Okay? So this lambda axis must be from, let's say if we are talking about MAB, okay, moment about force F about axis AB, so lambda must be from A to B, okay. And if we are talking about moment at the point can be any point on top of lambda AB. It can be MA or MB or something in between, right? So moment about axis, which is a scalar value, is equals to unit vector of that axis, which is a vector, dot product with moment of point about an axis, moment of force about any point on that axis. Okay, so if we want to refer back to our previous example, okay, let's say we have calculated moment at point B, right? Okay, if we want to know what is the moment about AB axis, okay, this is a vector, this is a scalar or magnitude, right? The moment about AB axis must be equals to unit vector along AB. Okay, so that unit vector must be from, if we want to know AB, must be from A to B. Okay, if we choose B to A, the value will be the opposite, or it will be different. Okay, so MAB equals to lambda AB dot with moment about point on axis AB. Okay, so it can be moment at A, or it can also be moment at B, or if we want to be fancy, let's say this is point E, okay, it will be also equals to lambda AB dot moment at E. Okay, it will still give you the same answer. All right. Normally, we will choose points that we have known. Okay, we will choose moment at points that we have known. For example, here, if the first part of the question is asking for MB, moment at point B, and the second part of the question is asking about moment about axis AB. So we will make use of MB that we have known previously. So we will choose this form of the equation. So moment about axis AB is equals to lambda AB dot MB. Okay, we don't want to calculate MA or ME, okay, because this is wasting time, right? Since we already know MB. So coming back to our uh, previous example, so let's say if we want to use MB, so moment about axis AB is equals to lambda AB dot MB. So lambda AB is a unit vector. Remember, this is not position vector. This guy is a unit vector. Unit vector. Unit vector means it has a magnitude of 1. So guys, unit vector. Okay. So if we want to calculate what's the value of lambda AB, okay, so all of these are vector quantities. This guy is not, is a magnitude, okay. So lambda AB is unit vector from A to B, okay, from A to B, okay. So lambda AB in this case will be equals to, we know the coordinate of A is along X 0, along Y 0, along Z is minus 1.2, okay. B along X is 2.4, along Y is minus 2.4, along Z is equals to 0, okay. So if we want to know lambda A to B, so it will be equals to lambda X over lambda I plus lambda Y over lambda J plus lambda Z over lambda A, okay. So what is lambda X? Lambda X is component of lambda AB along X. Lambda is the magnitude, or basically the length of AB, okay. So in that sense, lambda X will be equals to from A to B, so you have 2.4 I, lambda Y is equals to minus 2.4 J, lambda Z is equals to 1.2 K, right? And lambda is equals to 2.4 squared plus 2.4 squared plus 1.2 squared. So we have lambda equals to 3.6, right? So this is our lambda vector. Once we have our lambda vector, so MAB is just equals to lambda AB dot product with MB, okay. So again, this lambda AB as a component along IJK, so we have 2.4 over 3.6 I minus 2.4 over 3.6 K plus 1.2 over 3.6 K dot product with MB, okay. To be general, let's say MB as a component along I, component along J, component along K, okay. Since we have not calculated this before, it's okay, just leave it like this. What we need to know is for dot product, we will have values only when we dot I with I, J with J, K with K, okay. So you have values here, and the values is 1, 1, 1, okay. For the rest, for the other combination, the value is equal to 0, okay. So remember that. That means in this case, for the value along I, take this part, multiply with this part, okay. Value along J, take this part, multiply with this part. Value along K, take this part, multiply with this part, right? And just sum them up together to get the magnitude of MAB. Clear? Alright? Okay. If you are clear, so you are ready to solve any problem in 3D. Okay. So for example, in this question, we have force F equals to 700 Newton acting along line CD and want to determine the moment of F about OA axis. Okay. So what's the strategy? Okay, this is the F, right? And want to find the moment of this F about OA. So we want to find MOA, which is equal to lambda OA dot product with moment of any point on top of this OA axis. So where's OA? A is this axis, right? Okay. So we want to find moment of this force on any point on top of this OA axis. You can choose point O or point A. If I'm the one doing this question, I will always choose point O because it is the simplest, right? Compared to A. Okay. So the force vector must be, remember, must be from O to the line of force, right? Okay. So in this case, I am choosing point O. And to solve this, we have to know these two first. Okay. I will be solving for MO first, moment at point O, due to this force F. And this will be equals to R from point O towards the line of force. Okay. So from O to the line of force, I can choose O to C or O to D. And I will always choose O to D because O to D is much simpler. Okay. And this is crossed with the force vector F. All right. So we will be solving MO first. So F in terms of IJK will be equal to its magnitude 700 times. In terms of coordinate, D is equals to along X is 0.2, along Y is 0, along Z is 0 again. Point C in terms of magnitude, along X is 0, along Y is 0.3, along Z is 0.6. Okay. So based on this coordinate, we know that 700 is equals to equals to 700 times dx over d I plus dy over d j plus dz over d. Okay, so 700 dx is, our force is from C to D, so x must be 0.2 minus 0, so you have 0.2. We'll be calculating d later on, plus dy 0 minus 0.3 j plus dz is 0 minus 0.6. What is it? Okay. The force vector is from C to D, right? C to D. Okay, from C to D. If you want to visualize it, imagine yourself sitting at C. Now you want to move from C to D. So along X, the motion will be equals to 0.2, right? So you are moving 0.2 meter along X. And it is along positive X, so that's why you have positive value. Okay. Along Y, from C to D, you are basically moving downward. By how much? By 0.3. Okay. And moving downward is along negative y-axis. So that's why you have negative sign here. It is 0.3. And along z-axis, again, from C to D, you are moving along negative z-axis. Okay. You're starting from C to D. Make sense? Okay. Or in mathematical form, if you are moving from C to D, always use the coordinate at the end point minus coordinate at the starting point. So you have 0.2 minus 0 for dx, dy 0 minus 0.3, so you have minus 0.3 here. And for dz, you have 0 minus 0.6, so you have minus 0.6. Okay? So you have multiple choice in understanding what's happening there. So for d, it is equals to 0.2 squared plus 0.3 squared plus 0.7. Okay. Right? So I'm going to leave it at this point. So this is our f. Now we want to find what is our ROD. So ROD is very simple. Okay. From O to D. Okay. So the position vector. Okay. Remember what's the difference between position vector and unit vector? position vector does not need to have a unit value as its magnitude. Okay, unit vector need to have 1 as its magnitude. Okay, position vector does not need to have 1 as its magnitude. Okay, so for position vector OD, it will be equals to the distance, okay, which is 0.2. And since this distance is along x, okay, so you have 0.2 I. No distance along y and no distance along z. So that's it. That's your ROD. Okay, as simple as that. And the magnitude does not need to be 1. Right? If you refer back to what we have learned so far, f is actually can be written in terms of its magnitude times a unit vector. Okay, f is a vector quantity, so it can be represented by magnitude and direction. So this unit vector represent direction actually. Okay, so this is the unit vector for unit vector for f actually. Okay, that's why the magnitude here, if you calculate, it will be equals to 1. All right. So coming back to our MO, since we have only item here, and we know we need to do cross product, ijk, and cross product will be equals to a value if we cross I with j, I with k, and not I with itself. So I must be crossed with j and k, not with I. Okay, so here the moment at O will be equals to 0.2 times this guy here. So I, j will give you positive k, done. And then I was with this guy, I, k will give you negative k. So here we have 0.2, 700, and then here minus 0.6 over 0.7, negative k. Sorry, ij will give you k, ik will give you negative j, my bad. Right? So once we have this, we can, right? Once we have MO, we can move on to determine what's MOA. Okay, so lambda OA is unit vector from O to A. O to A. Okay, so the unit vector here will be equals to lambda x over lambda I plus lambda y over lambda j plus lambda z over lambda a. Right? So along x, from O to A, along x, it is moving 0.2. So 0.2 I will be calculating lambda later on. Lambda y is not moving along y, it's 0 over lambda plus lambda z. Along z is moving from O to A, 0.4. Okay. Okay. So the lambda is equal to 0.2 squared plus 0.4 squared. Out of that, we have 0.44. Right? So this is lambda OA. So moment about SSOA is just equals to lambda OA or 0.2 over 0.44 I plus 0.4 over 0.44 A dot product with our MO. So MO is equals to this term here, 0.2 times 700 minus 0.3. Guys, okay. Okay. As before, dot product will be equals to 1 when it multiplies with itself. So I must be multiplied with I. No I. So gone. Don't waste your time. Okay. So you have only A part. Okay. J will not be multiplied with anything. Gone. So this part will be equals to 0.4 over 0.44 times 0.2 times 700 times minus 0.3 over 0.7. Okay. So this will give you moment about OA in terms of Newton meter. And it is a magnitude. Okay, you don't have IJK in front here. Alright? Clear? Any questions so far? Clear? Okay, hopefully clear. So basically for this lecture we have covered all related to moment. Okay, so we have covered moment about a point in 2D, moment about a point in 3D, as well as moment about axis in 3D. Of course, you get better understanding if you try to solve the question yourself. Okay, clear? All right. Okay, if everything is clear, I'll stop the class uh, today. So we'll see you again in next class. Okay, stay safe. All right. Assalamualaikum warahmatullah. Thank you, everyone.